Okay, thanks very much for the opportunity to speak here. So this is a sequence of works with various people. Efrat Gershkovitz from the Weizmann Institute, she's a student. Jaume Gomes, Poshen Sin, he's a student at the Institute for Advanced Study. Nafitz Ishtiak from the Perimeter Institute. Avner Karasik from the Weizmann Institute, and the others you probably know. Yifan Wang is moving to Princeton University now. The context of these works is that while we're not going to be studying planar theories, so we're going to be studying finite n gauge theories. And for this finite n gauge theories, there are some special correlation functions which also admit some structure of integrability. They can be computed exactly. So it's different from perhaps the usual studies of integrability in planar theories. Here, integrability shows up in non-planar theories. But of course, it would be too much to expect that it would be correct for the full theory. So we're only exploring a special class of operators for which integrability seems to take place. These are the Coulomb branch operators. So also, if there are any urgent questions during the talk, before the question session, please stop me. So my main purpose is to address some issues in n equals 2 supersymmetric theories in 4 dimensions mostly. But at the end of the talk, I would also make comments about some two-dimensional analogs of these questions. These are problems that have been standing for some years, but with the advent of some new methods like localization and other various new understandings of anomalies, these problems can now be solved. So we will be studying some correlation functions of well-defined operators in n equals 2 theories, and there will be some exact expressions for these correlation functions, and it will be possible to prove that there is some structure of underlying integrability. And this would also allow us to test many ideas about the Borel summability of perturbation theory in quantum field theory, Padé approximations, various connections with mathematics, and also the bootstrap program. So there are many actually references to connections between what I'm doing and the bootstrap program, which I haven't added to the slides. But in particular, since Eli Pomone is here, you can talk to Eli and ask her about the various connections. I'll make some additional comments about that. So in n equals 2 superconformal filters, there is a special class of operators. These are chiral operators, which are annihilated by both right-moving supercharges. For this special class of operators, we will refer to these operators as Coulomb branch operators, because there is some interpretation of these operators. When they get expectation values, you break the gauge symmetry to some U1s. But in any case, the operators are defined abstractly by being annihilated by the right-moving supercharges. And for such representations, there is a simple connection between the dimension of these operators and their R charges. So this is common for a half BPS operators. So these operators are half BPS, as you see. So their dimensions are given in terms of their R charge. Now, if you want to be slightly unfair and slightly shallow, you can summarize the Seiberg-Witten theory and all of these developments of that sort from the 90s by saying that what Seiberg-Witten and analogous developments have achieved is that they've determined the one-point functions of these operators as a function of the vacuum manifold. So these theories, n equals 2 theories, have typically lots of different vacua in addition to the conformal point. And essentially these holomorphy methods and Seiberg-Witten methods have allowed to compute purely holomorphic correlation functions. So by purely holomorphic, I mean products of chiral operators evaluated in the vacuum. So that's what essentially the physics of supersymmetric gauge theories in the 90s has achieved. What I'll be interested in here is to study the first non-holomorphic observable, or the minimal non-holomorphic observable, slightly analogous if you want to NMHV in scattering amplitudes. So this is a correlation function that involves an arbitrary number of chiral operators, Coulomb branch operators, but there is also exactly one anti-chiral operator inserted at some point. So this is some correlation function conformal field theory that depends a priori on n+1 points. N of them are chiral operators, and one of them is an anti-chiral operator. So n of them are Coulomb branch operators, and one of them is an anti-Coulomb branch operator. So this is the minimal non-holomorphic observable in the theory. This is the minimal observable that could depend non-trivially on the coupling constants of the theory. And the question is whether we can determine these correlation functions exactly. Now, for these correlation functions to be non-vanishing, there is a very simple superselection rule, which is that the sum of the dimensions of the chiral operators has to be equal to the dimension of the anti-chiral operator, because they are charged under the R symmetry. So you want the whole thing to be neutral under the R symmetry. Now, this correlation function is to be computed at the origin of the moduli space of vacua, namely at the conformal fixed point, not on the Coulomb branch. You could also try to compute this correlation function on the Coulomb branch. That would be an interesting exercise, but here I'm just going to focus on this correlation function at the fixed point of the RG flow. So in order to have some examples in mind and for reference, you can first imagine doing this exercise in n equals 4, which is a special case of n equals 2. So in n equals 4, there is a nice theorem it's a suggestion that later became into a theorem by Limin, Waller, and Gamani and Seiberg, and later their suggestion was rigorously proved. So what they claimed is that in n equals 4, these minimal non-holomorphic observables, namely extremal correlators, so I'll be referring to these minimal non-holomorphic observables also as extremal correlators, that's how they call them. So these extremal correlation functions were claimed to be exact at tree level. So it's true that they are non-holomorphic, but they're also kind of boring because they're exact at tree level. And that's true for any n, not just in the planar limit. So these correlation functions can be computed exactly for any n. And people have used this observation to compare that with various supergravity results. Because now that you know the 3-point functions of chiral, chiral, anti-chiral, you can compare that to some vertices that appear in supergravity on ADS 5 times S5. And these were some of the first non-trivial checks of the ADS CFT correspondence. So in n equals 4, this situation is very simple, because these correlation functions are exact at tree level. Sorry, it has died. I'll just use that. No. I think the battery ran out at the worst possible. Yeah. I think. Oh, now it's working. Yeah. Okay. So the second example to keep in mind, this example is more interesting, is Seiberg-Witten theory, which is a genuine n equals 2 theory. It's not n equals 4. So let's say that we start from Seiberg-Witten theory with an SU2 gauge group, just for simplicity. So that's a SU2 gauge group with 4 fundamental hypermultiplets. It's a conformal field theory. Now, the space of chiral operators, of Coulomb branch operators, is very simple. The space of Coulomb branch operators are just traces of the scalar in the vector multiplet squared, and that trace is raised to an arbitrary power. So there's a single trace operator and then multi-trace operators where you start from trace phi squared and raise it to any power. And that's a complete set of Coulomb branch operators that are annihilated by all the Q bars. Now, in this theory, there is also a coupling constant, very much like in n equals 4, which is given by this tau. And the chiral ring relations are very simple. So it's evident that if you just multiply ON and OM, you get ON plus M. So the chiral ring relations are very, very simple. And you can normalize, there is a preferred normalization of the operators where the coefficient on the right-hand side is just 1. So once you normalize the operators in this way, that the chiral ring relations are that ON times OM is ON plus M, it makes sense to ask what are the 2-point functions, because now the normalization of the operators is completely fixed. So you can ask what is ON with ON bar, and you can call this function G to N of tau and tau bar. So it's a non-trivial function of the coupling constants. And there is a function for any n. For different n's, these functions may not be related to each other. And once you know the chiral ring relations, and once you know these 2-point functions, I will soon give an argument that all the extremal correlation functions are now fixed. So the space of Seiberg-Witten theories, this tau lives in the fundamental domain as usual. And in fact, the first instance of this function G2n that I've mentioned, namely G2, has an interesting interpretation. G2 is just the metric on the space. So G2 is like the metric on the space of theories. Our space of theories is given by this fundamental domain. And the metric on the space of theories is given by the two-point function G2. So the special case with n equals 1 has an interesting specific interpretation, geometric interpretation. So the interesting, perhaps, surprise is that unlike in n equals 4, these correlation functions are not saturated by tree-level diagrams. People have computed these correlation functions perturbatively in the 90s, and more recently there was a beautiful work by Baggio, Niarchos, and Papadodimas, which made many substantial improvements. So in particular, I've quoted here the first few orders, that you find if you expand around weak coupling. So the metric on the space of theories in Seiberg-Whitney theory is not quite the Poincare metric, as in n equals 4. It's not saturated by tree-level diagrams. You see that there are interesting corrections with some zeta functions that appear, and you can compute them with Feynman diagrams, and you can check that these results are correct. So this is the first non-trivial case that you would like to solve. You would like to compute exactly these 3-point functions or 2-point functions for chiral, chiral, anti-chiral operators, and you see that there are non-trivial functions of the coupling constants. Another example that you could keep in mind is not just SU2 Seiberg-Whitney theory, but SUN Seiberg-Whitney theory, where there are 2n hypermultiplets in the fundamental representation. And now the chiral ring is very slightly more complicated, because the chiral ring is not generated just by trace phi squared to an arbitrary power, but you can have trace phi squared, trace phi cubed, trace phi to the 4, and all of that you can raise to an arbitrary power. So in total, there are n-1 generators, and you can raise each of them to any power you want. It's a freely generated chiral ring. Incidentally, I can make a comment that there is a conjecture that the chiral rings in n equals 2 theories in 4 dimensions are always freely generated. So the chiral ring relations are always supposedly very simple. Okay, the metric on this space of theories for SUN is still given by the 2-point function trace phi squared bar. So that still would measure the metric on the space of theories. So this is always true, that the 2-point function of the operators of dimension 2 measures the metric on the space of theories. And you can ask if there is an interesting or useful interpretation for the other correlation functions between Coulomb branch operators. So you can mathematically show that these other correlation functions can be viewed as a holomorphic vector bundle over the space of theories. So the space of theories has some canonically defined holomorphic vector bundle, and these other correlation functions can be viewed as a Hermitian metric on this vector bundle. And mathematically, this is a very natural construction that I can make comments about at the end if people are interested. So mathematically, these kind of things appear very naturally. Now, another comment that I wanted to make, so that everybody's on the same page, is that if we know the 2-point functions, which I've discussed a little bit, and if we know the chiral ring relations, which I mentioned are supposedly very simple because the chiral ring is supposed to be freely generated, then one can, from that, fix all the extremal correlators. So any number, so you can fix the correlation functions of any number of Coulomb branch operators and one anti-chiral operator. And the idea is that you can put the anti-chiral operator without loss of generality at infinity, and then you can prove a word identity that now nothing depends on the axis, and so you can collapse everything by using chiral ring relations into a 2-point function. So once you know the chiral ring relations, which we believe we know from the works of the 90s, and once we've computed the 2-point functions, all the extremal correlators are fixed. So the idea is that we can therefore focus on 2-point functions with this preferred normalization of the operators. So what's the idea? How are we going to attack this problem of computing these extremal correlators in n equals 2 gauge theories? The idea is that we will try to put first the theory in compact space so that we can compute some partition functions using localization. And the compact space which is most natural for this problem is the sphere. As you'll see, the sphere has many nice properties that make this computation feasible. So you put the theory on the sphere, and as you know, for conformal field theories, there is a natural way to put them on the sphere because the sphere is conformally flat. So you can take a conformal field theory and compactify it on the sphere in a canonical way by doing a Wild transformation. So there is a unique way to put n equals 2 theories, conformal n equals 2 theories on the sphere. In fact, any conformal field theory can be put on the sphere in a unique fashion. But there are extremely important anomalies. So this is now going to be a subtle discussion of trace anomalies in field theory. But this is absolutely crucial in order to understand how to extract these interesting correlation functions from the sphere, and in order to discover integrability. So this discussion of anomalies may seem pedantic, but it's extremely crucial. So conformally, the sphere and flat space are the same. And you would think that if you take a primary operator, a primary of the conformal group, then its image on the sphere is very simple. They are just related by some wild rescaling, the two operators on the sphere and in flat space. However, this intuition is not completely correct. So let me explain why. So first of all, imagine that we take our conformal field theory, which is described by some action S, and we deform it by some background fields, which are the coupling constants, multiplying the operators OA. So this now allows us to define some generating functional Z, and derivatives of this generating functional Z would compute correlation functions in flat space. So this is just a way to define a generating functional by making the coupling constants into space-dependent functions. Now, if you take these derivatives in the denominator of the left-hand side to be at different points in space, you get a correlation function at separated points, completely unambiguous and completely UV finite. But actually, if you now try to study the theory on the sphere, there is some ambiguity that you encounter. Let me give an example. Let's imagine that there is an operator OA. Let's imagine that one of these operators, OA, has dimension 2. Therefore, the corresponding background field, tau, would have dimension 2, canonically associated to it. And therefore, if we put the theory on the sphere, we can also add a coupling which looks like the Ricci scalar times tau 2, where the superscript 2 means that it has dimension 2. So this is a marginal coupling that you can add. Now, from the point of view of a person in flat space, this is some kind of improvement, boring improvement transformation, because tau 2 is a background field, and R is just the curvature. So that means that there is some contact term when you bring the energy momentum tensor close to the operator O. And that's completely unphysical if you're a flat space person. But if you want to make computations on the sphere, that may become consequential, because now the one-point function of O2 in curved space would be equal to the Ricci scalar of the sphere. Now, O could be a primary operator. So you could think that the one-point function of primary operators on the sphere should be vanishing because they're related by Wild transformations to their one-point functions in flat space. So you see that this is not completely correct because one has to worry about mixing between operators whose dimensions differ by 2 or any multiple of 2. So in general, an operator of dimension delta can mix with operators of dimension delta minus 2, delta minus 4, delta minus 6. There can be a general mixing matrix, which is completely undetermined. So it's completely ambiguous. And so when people say that primary operators on the sphere are just the image of the corresponding primary operators in flat space, what they mean is that there is a scheme in which this is true. And the scheme is such that all these coefficients alpha 1, alpha 2, and alpha 4, alpha 3, and alpha 4 vanish. So it's just a scheme. The surprise is that in n equals 2 superconformal field theory, such a scheme doesn't exist. The scheme exists if you don't have supersymmetry, but when you have supersymmetry, the scheme may not exist because the corresponding scheme, because the corresponding counter terms that you may need to add may actually involve non-local terms upon supersymmetrizing them. So we claim that in n equals 2 theories, there is no scheme in which this mixing is absent. So this mixing is necessary. It's part of the game. And in fact, this mixing is interesting. It computes interesting geometric data about the space of theories. So let me give an example. This is going to be slightly technical, but you're not supposed to understand the formulas here. But the moral should be more or less clear. So if you take an operator of dimension delta equals 2, and you want to demonstrate that there is no scheme in which this mixing is absent, so what you do is that you try to write down a counter term that would eliminate the mixing, and then you try to supersymmetrize it. And once you supersymmetrize it, you find that you also need to add non-local terms. And once you add non-local terms, it's no longer a counter term. And in fact, one can show that the mixing is related to the Kähler potential in the space of theories. So it's related to the Zamolodchikov metric in the space of theories. So you can demonstrate very explicitly, it's a long argument, but one can demonstrate very explicitly that the mixing in n equals 2 between, say, the unit operator and some operator of dimension 2 is not something that you can remove by a scheme transformation. It's physical and it's related to the geometry in the space of theories. So the conclusion that you may try to remember is that the sphere compactifications induce in general some mixings, which cannot be removed by scheme transformations. And when you translate computations from the sphere to flat space, you have to be extremely careful about removing these mixing effects. So you need to use something like a Gram-Schmidt procedure, which is sort of a natural algorithm in linear algebra to remove mixings between vectors and vectors of lower grade. So let's start from SU2 super QCD. It could be n equals 4 SU2, or it could be n equals 2 Seiberg-Witten theory. It doesn't matter. What I'm going to use now is that there is just one operator that generates the chiral ring, which is true both in n equals 4 and in n equals 2. So if you want to compute correlation functions on the sphere, it's actually pretty easy. But as I said, correlation functions on the sphere have nothing to do a priori with correlation functions in flat space due to these mixing anomalies. But if you want to compute correlation functions on the sphere, you put one operator at the north pole, you put the other operator at the south pole. So trace phi squared to the power m would sit at the north pole, trace phi squared bar to the power n would sit at the south pole. And if you knew the partition function on the sphere of the theory, you could obtain that two-point function by derivatives of the partition function. So you take n derivatives with respect to tau, n derivatives with respect to tau bar, and you would get a two-point function on the sphere. And this partition function is known explicitly from the works of Peston on localization. However, this partition function has nothing to do with the two-point function in flat space because of anomalies. And in particular, you can take the Peston partition function and check that it's not diagonal in M and N. And the two-point functions in flat space have to be diagonal in dimension. Actually, this equation that we found where you relate this two-point function at the north and south pole and derivatives of the partition function is very non-trivial. The standard thing that you would expect when you take a derivative of the partition function with respect to some coupling constant is that you would lower the top component, integrate the top component of the corresponding superfield, while we're interested at localized bottom components of the corresponding superfields. So one has to do a lot of massaging in supergravity using conformal supergravity to prove that this identity is true. I'll try to give you now some intuition for why this identity is true. So the standard story in supersymmetry, if you take a derivative with respect to a coupling constant, would be that you lower an integrated top component. And then if you take a derivative with respect to some parameter and its conjugate, you would get a two-point function of integrated top components, f and f bar. Now in supersymmetry, f is usually the q squared of some other operator of the bottom component of the corresponding multiplet. And so it would seem that this correlation function just vanishes because f is q squared of something and q squared annihilates f bar. However, the point is that the fourth sphere is so suitable for this story because on the fourth sphere, it turns out that no section of the spinor bundle is without zeros. So there is always a zero for q squared. There is always a place where the spinor vanishes. And so this equation that f is q squared of something is not quite true. It's true almost everywhere, except at one point. And then this manipulation that would naively suggest that this two-point function vanishes is not true. You get a contribution from this one point where the section of the spinor bundle is non-vanishing. And then when you do the argument very carefully about what happens near that point, you find that you get a two-point function of the bottom components of the corresponding superfields. And that's why this equation that we conjectured is true. So now the question is, how do we go from these two-point functions on the sphere, which we've agreed are given by derivatives of this fourth sphere partition function, to flat space correlation functions? So to go to flat space correlation functions, one has to remove these mixing anomalies that I referred to. So one has to invoke a Gram-Schmidt procedure. Let's see how that works in the simplest example, where we try to disentangle the mixing between the unit operator and the first generator of the chiral ring, which is the dimension 2 operator. With the generator of the chiral ring, which is a dimension 2 operator. So let me explain carefully what's written here. So if you want to compute the expectation value of the unit operator, that's just 1 over the partition function times the partition function, which is 1. So that's trivial. Now the one-point function of the generator of the chiral ring, trace phi squared, is given by the first derivative of the partition function. And as I said, on the fourth sphere, this is non-trivial because of the mixing anomaly. So the one-point function of some primary operator is non-vanishing on the sphere. And then the two-point function of the sphere is given by the second derivative of the partition function. So we have a matrix of derivatives of the partition function, and we need to disentangle the mixing. And we do that by doing by the Gram-Schmidt procedure. So to get the two-point function in flat space, notice now we're talking about the two-point function in flat space. This is in R4, and that's the object we're really interested in. We take the determinant of this matrix. This is the suggestion. So we take the determinant of this matrix, and by taking the determinant, we've disentangled the mixing anomalies. The determinant of this matrix you can check. It's a small calculation. It's just the second derivative of the logarithm of the partition function. It's just a trivial identity using the chain rule. And so we find that the two-point function in flat space is given by the second derivative of the logarithm of the partition function. And therefore, the partition function is an exponential of the Kähler potential in the space of theories. So we see that the four-sphere partition function has an extremely beautiful interpretation. A priori, when Peston, computed it, the interpretation of that object wasn't clear. But here we've shown that this is just the exponential of the Kähler potential in the space of theories. And from the Kähler potential, you can obtain the Zamolodchikov metric. And therefore, you can obtain the exact expression for the metric in the space of theories. Actually, this formula has various topological consequences and not just consequences for the perturbative expansion. So from that formula, we see that the Kähler potential, which is normally not a well-defined object, because there are Kähler transformations when you go from patch to patch on a Kähler manifold. But we see that this formula implies that the Kähler potential gotta be physical, because otherwise this formula wouldn't make sense. And in fact, this has an implication that the Chern class of the Hodge bundle of the space of theories vanishes. This can be checked in examples, and it's actually pretty far-reaching. It has pretty far-reaching mathematical consequences for the moduli space of varieties. Also, one can use that to compute exactly whatever we want about this two-point function of phi squared in Seiberg-Witten theory. So this is, for example, the expansion in the one instanton sector that we can now compute just by doing this procedure. And there are also various connections with the theory of Riemann surfaces. Now, this determinant formula generalizes. So it's not just about trace phi squared with trace phi squared bar. As I told you, we're interested in the full set of extremal correlators. So we need to know the two-point functions of trace phi squared m and trace phi bar squared to the power m. So it's diagonal in m and n, so only when the two have to have the same power of m. And we're interested in this two-point function in flat space in R4. So the generalization of this Gram-Schmidt procedure shows that this is given by ratios of determinants of some matrices, big matrices, with the derivatives acting on the partition function. So we see that, this chiral ring, the extremal correlators are basically given by ratios of huge determinants of some derivatives acting on some functions. So this kind of formulas appear not just in SU2, they appear in any n equals 2 gauge theory. It follows from the fact that there are these anomalies, and it follows from this identity that relates derivatives of the partition function to correlation functions at the north and south pole. Now, for people who work in integrability, it's, of course, natural that such ratios of determinants would be related to integrable models. People have observed many years ago that ratios of determinants of some derivatives of some functions, they describe solutions, solitons of systems like Toda chains. And that's where the connection of this story to integrability makes an appearance. So I'll tell you which integrable models are underlying n equals 2 gauge theories. The extremal correlators of n equals 2 gauge theories. We haven't been able to identify the most general integral model that governs the extremal correlators of n equals 2 gauge theories, but in some special cases we could identify them. They have a name. These integral models have a name. So in SU2, which is the case that I have just discussed, whether it's n equals 4 or n equals 2, you get a Toda chain, a standard Toda chain. So the ratio of determinants that appears in n equals 2 in SU2 gauge theories is just a standard Toda chain. And this is in agreement with results of Bajaj and Yarkos Papadodimas and earlier results of Papadodimas about Tt star equations. So one can transform this. So if one takes the two-point function that we were interested in of trace phi squared to the power n, trace phi bar squared to the power n, and one defines this variable qn, then it disobeys the equations of motion of a Toda chain with a boundary condition. So it's an open Toda chain. And the only difference between n equals 4 and n equals 2 SU2 gauge theories is in the boundary conditions on the open Toda chain. So once you solve the Toda chain, you have solved all the extremal correlators of SU2 n equals 2 gauge theories, like Seiberg-Witten theory, or n equals 4. More generally, every n equals 2 gauge theory gives some kind of Toda chain. You can prove that using these ratios of determinants. You can find the Lux pair. So there is some integral model that is underlying any n equals 2 gauge theory, at least for this the extremal correlators of n equals 2 gauge theories are given by some integral model. This can be proven. The case of n equals 4 is, the case of n equals 4 is particularly simple. One gets infinitely many decoupled Toda chains in the general case. The case of SU2, Seiberg-Witten theory, I mean the theory is 4 hypermultiplets, is the one that I've just discussed. It's a half infinite Toda chain with some boundary conditions. It's solvable. The solitons are known. They're given by these ratios of determinants. Now, what happens in super QCD, meaning the theory SUN gauge theory with 2n hypermultiplets, is not yet known. It's known that it's integrable because this was proven, but it hasn't been identified by name. One can see that one essentially gets infinitely many Toda chains. One gets infinitely many Toda chains with some coupling. So unlike n equals 4 SUN gauge theories, n equals 2 SUN gauge theories with 2n hypermultiplets correspond to some system of infinitely many Toda chains which have some coupling. And we haven't been able to identify the systems by name, but one can compute the couplings between the Toda chains because of these determinant formulas that I've shown you. So using these determinant formulas, one can actually compute, for example, the 2-point function of trace phi cubed, trace phi cubed bar. That's no longer the Zamolodchikov metric. That's some element of this holomorphic vector bundle. And one can compute the expansion coupling to any order one wants. One can put it on the computer and obtain as many orders as one would like by this formula for the ratios of determinants. But we haven't been able to identify this specific integral model by name. It looks like some sort of coupled infinite Toda chain system. So an interesting conjecture about the perturbative series in quantum field theory has been that the Padé approximations converge. That's something that people used in QCD to compute higher loop beta functions. So there was always a competition between people who estimate higher order beta functions by using Padé approximations and people who actually compute them. And the differences tend to be smaller and smaller as you look at higher orders. So we, just for the fun of it, we checked whether this is true for this perturbative series in SU3 gauge theory for trace phi cubed bar. It's some non-trivial extremal correlator in SU3 gauge theory. And we played this game of trying to determine the next order by a Padé approximation and compare that to the actual next order that you can get from this ratio of determinants formula. And you see that there is a very nice convergence at higher order. This is like order 17 perturbation theory. And you see that there is a very nice exponentially fast convergence. It's actually exponentially fast. So let me summarize the story about 4-dimensional n equals 2 theories. I've just given you some small part of the story, but perhaps that was enough. So the problem of extremal correlators is now solved not just in n equals 4, but it's solved in n equals 2. All the extremal correlators in n equals 2 gauge theories are known. There is an algorithm that has these steps that I outlined, which allows you to solve them. There is some underlying story about anomalies that is very interesting. Anomalies of correlation, anomalies that relate this, anomalies which make the relation between the sphere and flat space non-trivial. Now, there is always an integrable system of the Hitchin type that is underlying these extremal correlators. In some cases, we found it to be the Toda chain. In some other cases, it's not yet identified by name. One can use this to test various ideas about Padé approximations, Borel summability, poles on the Borel plane, instantons, and various things of that sort. More generally, resurgence theory. There are lots of applications for ADS-CFT. Using that, one can compute extremal correlators in Large-Yang-Mills theory with SU2. Large-Yang-Mills theory with n equals 2 supersymmetry. There has been a lot of progress on that recently. I forgot to add another bullet point outlining the connections with the Bootstrap program, mostly what Eli Pomoni and her collaborators were doing. So in particular, Eli and her collaborators have very interesting conjectures about the properties of the Riemann tensor and the Ricci scalar on this space. So let me just go back there. As I've mentioned, one can compute the metric on this space. This is the space of theories, exactly. And this metric has a lot of interesting mathematical properties. For example, in n equals 4, it's just the Poincare metric, and it has constant negative curvature. And there are many interesting properties. There are many properties that you could perhaps envision to be true even in n=2 gauge theories. For example, we have a conjecture that we're testing, inspired by something that Ellie Pomonian and her collaborators did using the bootstrap methods, that the curvature is always non-positive, even for general n=2 gauge theories. And also, one can perhaps formulate a natural conjecture that even though the space is non-compact, the volume is actually finite. These kind of conjectures are natural to test with bootstrap ideas, so there are lots of connections between this story and the bootstrap, which I unfortunately failed to.
So I think you're confusing the ladies in the DESI theory group. It's Magdalena Lemos and her collaborators.
That's perhaps true.
And I'm the collaborator.
That's perhaps true. I apologize if that's the case.
That's fine.
Yeah. I'm sorry for that. I should have done my homework better. But in any case, they have very interesting papers. I think the content is correct, right?
Yes.
Okay, so I'm sorry for that. I wanted to finish with some comments about two-dimensional theories. So for two-dimensional theories, the problem for determining these extremal correlators is partly solved by works from the 90s, BCOV and TT star geometry. But actually, it's very limited. I mean, this kind of methods that were used in the 90s allow to solve very restricted cases, while these more advanced ideas using localization and anomalies, and these new anomalies allow to explore a much wider set of questions. So in particular, for 2,2 theories in 2 dimensions, there is a general claim that the moduli space of theories, namely the space of theories, is a product of two Kähler manifolds. One that has to do with the chiral deformations of the 2,2 theory, and one that has to do with the twisted chiral deformations of the 2,2 theory. So we expect a product of two Kähler manifolds. That's the space of theories. So there are two copies of the fundamental domain in the simplest case. And you can ask, what is the metric on this space? What are the extremal correlators? The structure is mathematically different, but it turns out that one can still do that using the sphere compactifications. I'm going over that very quickly because I'm not going to do justice to this story anyway. One interesting difference is that the chiral ring in 2 dimensions is not freely generated. That's actually a consequence of Coleman's theorem, which people not always appreciate. Every generator in 2 dimensions must be nilpotent. Otherwise, there will be a violation of Coleman's theorem. But an operator mixing of the sort that I mentioned, this new anomaly, still take place. One still has to do Gram-Schmidt procedure. And one still encounters ratios of determinants, and one still encounters Hitchin-type systems when one, say, tries to compute correlation functions of some complicated Calabi-Yau sigma model, supersymmetric sigma model. One still has these topological consequences that the Chern class of the Hodge bundle vanishes. This is a non-trivial statement about the moduli space of Calabi-Yau manifolds that many mathematicians are interested in, and I believe that it has passed some non-trivial consistency checks. There is another part to the story which is now being written up with Sarbre, Goguri, Gomis, and Ifan Wang, which is that while for 2,2 theories it has been long appreciated that the space of theories is a product of Kähler manifolds, if you take simple models like the K3 sigma model or the Toro sigma model, one finds that the moduli space of theories is actually not a product of Kähler manifolds. One common thing to these examples, which should have been Kähler but are not Kähler, is that they have more supersymmetry than just 2,2. So we're now working on a paper where we are proving a theorem that the space factorizes into Kähler manifolds if and only if there is no extended supersymmetry. So that's a weird theorem, that we prove something about 2,2 theories, but when there is extended supersymmetry, these theorems fail. And we are trying to show that this is the only obstruction, that this can only fail if there is extended supersymmetry. But otherwise, these ideas should be true for generic Calabi-Yau sigma models. And for example, one can compute extremal correlators of the Hodge vector bundles corresponding to the metric on the Hodge vector bundles using these ideas. And that can be viewed as some generalization of Gromov-Witten invariance. Okay, so thanks so much. Super fast? Yeah. 40 minutes, yeah, 5 minutes more.
So this function k tau tau, is it, how does it apply? Is it given by some matrix integral?
Right. So
In terms of this matrix integral, what is the observable which you study? How does it look like in terms of the matrix model? Because a ratio of determinants should have some meaning in the matrix model as well.
So the observables that we're studying are, let's say, endpoint functions in flat space of operators at different points, chiral, 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 anti-chiral. And we have some algorithm to go from the matrix model, which by itself doesn't have a clear interpretation, to this correlation function, right? So you take the matrix model, generating functional.
So you can trace it back to matrix model.
Right, so you take the matrix model, you take derivatives of it, you take determinants of derivatives, you take ratios of determinants of derivatives. So we view the matrix model in the language of integrability. The matrix model itself can be viewed as the boundary condition for the TODA spin chain. And then I mean, these extremal correlators are like a soliton on the TODA spin chain. So the matrix, so it's not a convenient manipulation of the matrix model. You have to take derivatives and determinants and ratios of derivatives. You can do it, of course, order by simply expanding everything, but it's not a very natural procedure at the level of the matrix model, it seems. But still, it's correct. I mean, we've reproduced all the perturbative results in the literature. And it agrees with large N, ADS-CFT. It seems to, this procedure is, I think, without a doubt correct. So.
Do you expect some relation with the cyber-Witten integrable system or integrable systems arising in the Nekrasov-Chetashvili?
By cyber-Witten integrable system, you must have meant the Donagi-Witten story, or?
Well, the system described by the cyber.
Yes. Okay. Yes. So, yeah. So amusingly enough, TODA chains also appeared in the Donagi-Witten story for the integrable structure in cyber-Witten curves, but we haven't been able to find a clear connection. In particular, as I mentioned, in our case, TODA chains appeared in SU2 gauge theory, cyber-Witten theory, very naturally, but in SU3 you can view it as some coupled TODA chains. And in cyber-Witten theory, the integrable system was easier. So it's not clear if there is a direct relation. I think that's a fair statement. We tried to think about it, but we haven't been able to find a direct relation. Yes. Yes. So yeah, another thing that would be very natural to try is to map flat space to ADS rather than to the sphere, and then you study quantum field theory in ADS. But then, as you know, you have to add more data. On the sphere, everything is fixed because it's a compact space, and everything is fixed by Weyl rescaling. In ADS, you have to add more data. You have to specify the boundary conditions. And in fact, there are several choices for the possible supersymmetry, preserving boundary conditions. Now, of course, it could be that there are some very natural boundary conditions for which one could also localize the theory and find interesting results about quantum field theories in ADS space. But I don't think any of that has been really tried or successfully tried. But you have to be, the worrisome issue is the boundary conditions.
And there's one technical question about the normalization of the operator. It seems that the distance still frequent, multiplying the by e to the n as very constant.
Yes. So the comment that was made is that, let me just explain to the right. So you're making the comment that even if you fix the 3-point functions, the chiral ring relations, let me go back to that corresponding slide. So the comment is that even after, sorry, that has stopped working again. So the comment is that even after you fix the chiral ring relation to be On times OM equals On plus M, the 2-point function is still not completely fixed. That is correct. However, you can prove that that remaining ambiguity cannot depend on tau and tau bar. you can use supersymmetry for that. So that remaining ambiguity is very mild. You can think about it as a very mild ambiguity. There is some. You can also understand it at the level of the fourth sphere partition function as some counter term that cannot depend on tau and tau bar. You can understand this multiplicative ambiguity from the fourth sphere point of view, and you can see that it cannot depend in a non-trivial fashion on tau and tau bar. But it's correct. It's a technical point that I omitted from the discussion.
You mentioned that this correlator, the tau dependence of this correlator could be computed in terms of Feynman graphs.
Yes, certainly.
Could you describe
Yeah.
roughly what kind of graphs really contribute there? Probably most of them are as usual in the topological sector, but what kind of graphs really contribute there?
I can't answer that. The student at Weitzman has checked that previous perturbative computations were correct, and they agree with our method using localization. So we basically use localization to reproduce previous perturbative computations. We checked the diagrams to 2 loops to check that this coefficient 135 zeta 3 is correct. But I don't have any insight to what kind of diagrams contribute at higher order. We've never tried to look at that from the Feynman diagram point of view. Because basically we just saw that we can reproduce all the perturbative data in the literature, and we convinced ourselves that our method is correct, and it can be used to go to arbitrarily high order in a matter of seconds. So we never tried to understand if there is any interesting structure at Feynman diagrams at higher orders.